Welcome, friends, to Unit 10, Lesson 1 on exponential and logarithmic equations. Today's essential question, by the end of today's lesson, you should know how to solve exponential and logarithmic equations and use those to solve some application problems. So when we're solving simple equations using one-to-one and inverse properties, I just want to put this up there so that you don't overlook the obvious. In general, when we have an exponential equation, we're going to use logarithms to solve it. We're going to logarithmize it. That's not very mathematical, but that's what we're going to do. When you have a log equation, we're going to exponentiate it. We're going to use exponents to solve it. But don't underestimate the power of your brain. For instance, example 1. I don't think you need any fancy logarithming, exponentiating. You don't need any of that to solve it. 16 is a power of 2. So x is just equal to 4. Same with example 2. You can do really like fancy math, but in order to get 0, and this is a log 7, doesn't this need to be the natural log of 7? So x is just 7, and I could just look at it by watching it. If you are wondering, well, how did she get that? If you want to do the fancy math, you would notice that this is a subtract. So I could rewrite this using properties of exponents by taking the quotient. Well, this is base e, so I can think of this as e to the 0, because remember, a log is an exponent. So e to the 0 is equal to x over 7. E to the 0 is 1, and I can cross multiply to get x is 7. Similarly, on something like example 3, this is actually, you could think of it as exponentiating it. Remember, this means log base e of x. That's what that means. So if I rewrite this just in exponential form, so we are doing some exponentiating here. I have e raised to the negative 3rd power, because remember, my log is the exponent, and that's going to equal my value of x. And if I type that in my calculator, I have e to the negative 3rd power. So my final answer would be 0.049, approximately 0.05. And on example 4, same thing. I could exponentiate it. Remember that it is a base of 10. So if I rewrite it as 10 to the negative 1st, base is 10. Remember, the log is the exponent, equals x. I get a 10. All right, as a rule, don't forget, you can pause me, you can rewind me. You should be taking notes and taking this in as you go through. All right, let's solve using exponential equation. We're going to solve exponential equations. So in general, the two strategies we have is use the one-to-one property, or we're going to logarithmize it. Again, this is not a very mathematical word, but in general, you want to do its inverse property to get there. Example 1 is a prime example of you don't need to use fancy logarithming to solve it. We can use the one-to-one property. Basically, if you look at e to the negative x squared equals e to the negative 3x plus 4, this is an exponential equation. I have a base e. Equals means the same or equivalent on both sides. So in order for this to be equivalent, then the exponents need to be the same. So I need to find a value of x that causes the exponent here to be the same as the exponent here. So I set negative x squared equal to negative 3x plus 4. I've not mathematically done anything with the e's. I haven't divided them. I haven't multiplied them. I haven't logged them. I just don't need them to figure out my value of x, because x is located in the exponent position. I'm going to get the x squared on the other side. This is a quadratic equation, so I am going to solve by factoring. So I get x is equal to, get with the program. Let's try that again. X squared minus 3x plus 4, hold up. I don't think it does factor. It does not factor, so let's do some quadratic formula. X equals the opposite of 3 plus or minus the square root of b squared minus 4 times 1 times 4 all over 2 times 1. And we're going to notice that we are going to get 9 minus 16 under there. So this is an imaginary solution. So there are no real solutions for this problem. Example 2, we're going to logarithmize it. And I know this is not a mathematical term, but in this problem, let's talk through. If I have choices, I can use the one-to-one property or I can use logs to solve it. Before I make any kind of decision, I need to isolate. I look at my x, that's my exponential or my exponent. Its base is 2. You need to isolate that before you make any decisions. So I'm going to divide both sides by 3 to isolate 2 to the x. And that's going to give me what? 42 divided by 3 is 14. 14 is not a power of 2. So the one-to-one property would not be appropriate. What I can do, however, is take a log of both sides. Because remember, whatever you do to one side, you can do to the other. So this is what we mean by loginated. Now, just for the purposes of teaching, I could take the common log on both sides, and this is what I tend to do, because it's just the easiest button to push. You could take the natural log on both sides. You could take the log of your favorite number. I could take the log of base 15 on both sides. And you know what, while I'm doing that, let me fire up my TI Inspire so I can show this to you, because I'll need the Inspire in just a minute to prove that to you. But while I'm doing that, the point is that you can take any base you want to both sides. Why do we tend to use the common log or the natural log? Because scientific and 83 and 84 calculators, or in the past log tables, facilitated that for us. But really, if you have a TI Inspire and you feel inspired to be creative, you could take really the log of either of the sides. So now I'm going to use my properties of exponents. I have a power to a power, or my properties of logs. So I can rewrite this as the product. Okay, I can rewrite this as the product of x log 2 equals log 14. And then in order to get x by itself, I would divide by common log of 2. This becomes something that I input into my calculator. Okay, so I have the log of 14. Make sure you close the parentheses. Divided by the log of 2. So my final answer to this, and hopefully this makes sense, that if you think about 2 raised to the 3rd power is 8, 2 raised to the 4th power is 16. So if I'm trying to find a power that gives me 14, 3.8 seems like a pretty logical answer. Please notice that had I chose to do it using the natural log, I still have my power to a power, so those algebraic steps do not change. And I'm not going to do every type of log base on every problem. I just wanted to do a simple problem so that you can see that what base you pick is really irrelevant. I can do the natural log of 2, and I can divide that by the natural log of 14. Get with the program, not type it in correctly. Hello, sorry about that. The natural log of 14 divided by the natural log of 2. And notice how I still get 3.8. Okay. And then I could do it on the Inspire because it can handle other bases. Let's see. So I can do the log base 15 of 14, and I can divide that by the log base 15 of 2, and I still get 3.8. All right, moving right along. We have e to the x plus 5 equals 60. Remember, my strategies for solving an exponential are either the one-to-one property or I can use logs. Those are my strategies. So before I pick a strategy, I have to notice where is my exponent located and where is the base. So I have to isolate e to the x first. So I'm going to subtract 5 from both sides, and I have e to the x is equal to 55. Well, 55 is not an even power of e, so we're going to use logs on both sides. Again, you can choose to do a common log on both sides, but I want to show you why it's advantageous to use a natural log on both sides. The reason it's advantageous to use the natural log on both sides is when I use my power to a power, and I get x times the natural log of e equals the natural log of 55. The natural log of e is 1. Remember, the natural log of e means log base e of e. So what power of this e gives me this e, and that's 1. So I'm just left with the natural log of 55, and then I would type that into the old calculator. And so it's approximately, x is approximately 4. You can still use the natural log. I would have x times the log of e, technically to the first, and then I would divide, So I'd be the log of 55 divided by the log of e. And I just want to show you that even if you choose to do it in that way, if I take the log of 55 and divide it by the log of e to the first power, that you still get the exact same solution. So I think it's, it has its advantages to do the natural log of e, but please know that it still does not make, I don't want to do that, cancel. I was trying to bring this to the back so that it could, order. Send it back, there we go. So that it doesn't make a difference what base you pick on both sides. All right, let's look at example 4. Again, I think to myself, this is an exponential equation. My two strategies to solve it are the one-to-one or using logs. In order for me to determine which one, though, I have to locate my exponent, and it's on the base of 3, and I have to isolate that before I make any decisions about what strategy I want to use. So in order to isolate that, I'm going to add 4 to both sides. Then I'm going to divide by 2. Okay, 15 halves. And 15 halves is not a power of 3, so I'm going to use logs in order to solve this. I'm not going to use the one-to-one. Now, in this case, I'm just going to use a common log on both sides. So I'm going to do the common log of 3 to the 2t minus 5 to undo that, and the log of 7.5. Okay? Please be careful. When I bring this, remember this is a power to a power. I have 2t minus 5 times the log of 3 equals the log of 7.5. Okay? In order to get the 2t by itself, I'm going to do the log of 3 on both sides. So I have 2t minus 5 equals, and let's figure out what that value is. I have the log of 7.5 divided by the log of 3. Okay. So this gives me approximately 1.83. I encourage you to just keep that value in your calculator, because in order to get my final answer, I need to add 5 to it and then divide by 2. So my final answer is x is approximately 3.4. By just keeping that in my calculator, adding 5 and then dividing by 2, it kept it a little bit more exact. But 3.4 is an approximate answer. For those of you that like to check your answers, please remind yourself that 3.4 is approximate. So it's going to come out pretty close, but it might not come out exact when you go to check your answers. All right, so we have e to the 2x minus 3 e to the x plus 2 equals 0. This is a different kind of strategy. On this strategy, we are going to use logs, but I just want to let you know that something like this will be on the test. This is going to require the use of factoring. So this is kind of a special case, a special type of problem. If I asked you to factor x squared minus 3x plus 2, hopefully most of you would tell me it would be x minus 2, x minus 1. This is no different, except instead of an x, I have a base of e. So when I factor this, it's going to be e squared, wrong, not, hello, e to the x, e to the x, because e to the x times e to the x gives me e to the x plus x, which is e to the 2x. And then I have my minus 2 and my minus 1, because my outer term will be a negative x, my inner term will be a negative 2x, which yields a negative 3x squared. Then using the zero product property, I set each of those factors equal to 0. Okay. And again, these are exponential equations. So if it's an exponential equation, I can use the one-to-one, or I can use logs. Since we're dealing with e, nothing is really going to be a perfect base of e, so we're going to use logs. So I have e to the x is equal to 2, e to the x is equal to 1, and I'm going to log an 8. I'm going to take a natural log on both sides. And taking a natural log is a little bit more advantageous, because when I do x ln of e, this is 1. So one of my solutions is the natural log of 2. And my other solution is the natural log of 1. So there's my natural log of 2. There's my natural log of 1. Logarithmic equations. Again, when you're given a log in the problem, that's what denotes that it's logarithmic. And we're going to have the same thing. You can either use the one-to-one property or we're going to exponentiate them. Those are your choices. So in this problem, notice how this is set up. The log of something equals the log of something. Notice we have the same bases in the logs. So again, I'm not doing anything with the logs. I'm not dividing them. I'm not subtracting them. It's just the log of a value equals the log of a value. Those values must be the same by virtue of what an equal sign means, that it's equivalent on both sides. So I need to find a value of x that when I square it and subtract 2 is equal to x. That value will cause them to be the same. So I have x squared minus x minus 2 equals 0. I'm going to solve this quadratic by factoring. So I'm left with x equals 2 and x equals negative 1. This is where you need to be careful, again, of extraneous solutions. The reason you need to be careful is, remember with logarithms, you've got a domain restriction. And so if I put in 2, I would have the log of 2 squared minus 2 equals the log of 2. So this would be the log of 4 minus 2 equals the log of 2. And these are going to be equivalent because log 2 equals log 2. But if I put in negative 1, I have the log of negative 1, the quantity squared minus 2 equals the log of negative 1. And if you're doing the math, guys, you might be like, oh, well, the log of negative 1 equals the log of negative 1, so that's the solution. This is extraneous because, as a reminder, you cannot have a negative value. There is no power of 10. Remember, this is the common log. There's no power of 10 that yields negative 1. So my only solution is x equals 2. All right, so here I have the natural log of x equals 3, and I have two strategies. I can use the one-to-one, or I can exponentiate, okay? And that is a formal math term. Okay, I'm not going to use the one-to-one because in order for use the one-to-one, you're going to have the log of stuff is equal to the log of stuff, and I don't have a log on each problem here. So in order to exponentiate, that's exactly what you do. You rewrite it in exponential form. Remember, this implies base e. A log is an exponent, and that equals x. So all I have to do is type in e to the third. And so my final answer to this is 20. And remember, the natural log of 20.1 approximately equals 3. And 20.1 is an acceptable value behind the log because it is a value greater than 0. Okay, you're like, oh crap, what do I do on a problem like example 3? I've got all of these logs going on. This is where the last lesson, where your properties of exponents are going to come into play. Before I make any decisions, I've got to get rid of, in order, remember my strategies are the one-to-one or exponentiate. I have to figure out what I have to do with that subtract. I'm hoping, if you remember, if this is an exponent and this is an exponent, and I'm being asked to subtract, that means it's going to be a quotient because I subtract exponents when I'm taking a quotient. So I can rewrite or condense the left side into the log base 6 of 3x plus 14 over 5 equals the log base 6 of 2 to the x. In this case, I'm going to choose the one-to-one strategy because I have log base 6, and I just need to find a value of x that causes the values to be the same. So I have 3x plus 14 over 5 equals 2x. I'm going to use cross multiplication. So 10x is equal to 3x plus 14. So 7x is equal to 14. And so x is equal to 2. If I put 2 back into here, Or if I put 2 back into here, I get log base 6 of 20 minus log base 6 of 5 equals log base 6 of 4. And if I use my properties of logarithms, notice that these are equivalent and it's acceptable to have a power of 6 that gives me 4. So x equals 2 is my answer and life is good. All right, let's look at example 4. I have 2 log base 3 of 3x equals 4. And remember, when I have logs, I can use the one-to-one strategy or I can exponentiate. This is not a candidate for one-to-one because I don't have a log on both sides. But before I do anything, you have to remind yourself, well, I have 2 log base 3 of 3x. You have a couple choices here. You could rewrite this as a power, or you can feel free to just divide both sides by 2. Okay. Next, I'm going to exponentiate. So this means 3, which is my base. A log is an exponent. Squared equals 3x. So 9 is equal to 3x, and x is equal to 3. If you decided to do it in this manner, I would have 3 to the 4th power is equal to 9x squared. So 81 is equal to 9x squared. I would divide both sides by 9. So x squared is equal to 9. And I would get 3 and negative 3. But notice, if I inputted a negative 3 into the original, you would be taking the logarithm of a negative number. So that is extraneous. And I still get x is equal to 3 as a final solution. All right, let's look at example 5. Log of 5x. Let's see what I have written under here. Do all solutions work? We've already talked about extraneous solutions, so we're good. All right, moving on. Here, it's a logarithmic equation, so my strategies are either the one-to-one or I can exponentiate it. And you might be like, oh, there's 2 logs, I'm going to use the one-to-one. Well, before we determine which strategy we're going to use, let's take care of that sum. And remember, this is an exponent, this is an exponent. And when you're adding exponents, it means you are taking a product of their values. So I can rewrite this as log, it's the common log of base 10, of 5x times x minus 1, and that equals 2. I'm going to exponentiate this because I don't have it in the form of a log equals a log. So by exponentiating, it's base 10 raised to the exponent of 2 equals 5x squared minus 5x. Okay. So I have 0 is equal to 5x squared minus 5x minus 100. I'm going to divide everything by 5 because that's going to make my numbers lower. X squared minus x minus 20. I'm going to use factoring to solve. So I'm going to have x minus 5, x plus 4. And I get the solutions x is equal to 5 and x is equal to negative 4. But we need to check our answer. Certainly, if I put negative 4 back into either of those places, it's going to cause me to take the log of a negative number. So that's clearly extraneous. And then if I take the log of 25 plus the log of 4, will that equal 2? Well, this would be the log of 100, and certainly 2 is equal to 2. And life is good. All right, let's do some applications. You have deposited $500 in an account that pays 6.75% interest compounded continuously. How long will it take your money to double? So what we want to know is if we've deposited $500 in an account that pays 6.75% interest compounded continuously, I started with $500. And let's go back. Since I see the keywords compounded continuously, I'm going to use the model APERT. Okay. If I started with 500, they want to know when does it get to be 1,000. And my rate is 0.0675, but they want to know the time. So you have to solve this. This is an exponential equation. I don't see a log in it. My choices are to use the one-to-one property or loginate it. Since we're dealing with E, I'm probably going to use log to solve. Before I do that, we have to notice that my exponent is here. It's on the base of E. I have to isolate that, so I'm going to divide both sides by 500. Now that I've isolated the base, I can take a log of both sides. I'm going to choose to take the natural log since we're in base E. It's a little bit more efficient. All right, so I have the natural log of 2 equals 0.0675t times the natural log of E. Remember that the natural log of E is 1. So I have the natural log of 2 is equal to 0.0675t. So I just need to divide that. Let's type that in the calculator. So I've got the natural log of 2, and we're going to divide that by 0.0675. And so it's going to take approximately 10 years, 10.2, so 10.3. So about 10 years and 3 months. And our last example for today. The number of endangered animal species in the United States from 1990 to 2002 can be modeled by y equals negative 119 plus 164 natural log of t, where t is in between 10 and 22, where 10 corresponds to 1990 and 22 would correspond then to 2002. They want to know in which year did the number of endangered animal species reach 357. So if y represents the number of endangered species, 357 gets popped into our model. Now this is a log equation. So remember, you can use the 1-to-1 or you can exponentiate that. By looking at the problem, there's only one log. So the 1-to-1 is probably not what I'm going to use because I'm not going to have a log equals a log. In order to exponentiate, however, I'm going to have to isolate the natural log of t. So I'm going to add 119 to both sides. So what does that give me? 16, 5, 6, 7, 3, 4, 76. Okay. So then the natural log of t is going to equal 476 divided by 164. So that's approximately 2.9. Okay. So now I'm going to exponentiate. Remember, the natural log of t means that we're actually having an assumed base of e. So e, a log is an exponent, so that 2.9 is going to equal t. So again, to try to keep it the most exact in my calculator, I'm going to do e raised, and I'm just going to do the second answer, so it's going to take the answer from above. And so I get approximately 18.2. Now remember, it wants to know in which year did the number of endangered animal species reach 357. So we're looking about a year. 18.2 is not a year. But if 1990 represents 10, the 91 would represent 11, 92 would represent 12, 93, 4, 5, 6, 7, 8, and so on. So 1998 would represent 18. So sometime during the year in 1998 did this species reach 357. All right, so your learning opportunity that you can work on in class. Reminder, please go back and review, stop, pause, rewind. This is what you will have time to work on in class. I will also post an additional practice like I did in the last lesson that you can look at online. Thank you for listening and have a great day.